to do the test that's on Tuesday. And then Monday, we're going to do a bunch of practice with all this stuff. And that is, this space means do a drum roll. That is, I don't have it written down, but if I had it written down, it would say strong induction, because this whole time we would talk about weak mathematical induction, and now we're finally going to start talking about what the heck strong mathematical induction is. By the way, actually, let's do a little experiment here. I've been working on things. Check this out. You can write on the desk now. However, this feels really unlegible to me. Like, can you guys see this?
I can see it, but it's definitely fuzzy.
Yeah, it's fuzzy, right? That bums me out so much. I was hoping that would be like this. I was hoping this would be the new thing, because then I won't have to run out of space on the whiteboard. I just have a whole desk to work with. But anyway, we're back to the whiteboard. I have solutions. I have contingencies. So the point is, today we're talking about. Thank you for your honesty, by the way, Camille. Today we're talking about strong mathematical induction. And I have absolutely racked my brain trying to think of a nice physical example of this, but it's very hard. So strong mathematical induction is compared to weak mathematical induction. And let's go over what the heck weak mathematical induction was. Weak mathematical induction always went like this. To prove that some claim was true, P of n, for every number bigger than or equal to A, right? What you did is you first prove it for A, and then you showed that for anything bigger than or equal to A, if it was true for n, it would be true for n plus 1. So basically all you showed is that you found some number A that was true, and you proved that for everything including that and after that, if it's true for this, it's true for the next one. And it's true for the next one. So therefore it's true for the next one, the next one, the next one. And this was the whole thing we had with the dominoes, right? Where you had a whole line of dominoes here, right? And the whole thing about dominoes, the whole reason why we love that example so much, or at least I love it, but I hope I can speak for you and say you guys also love it. And that is that because this is a very nice physical way to think about what's actually happening in induction. What's happening is once you prove the base case, once you prove that that's true, well, this inductive step tells us that then P of A plus 1 is true, and then P of A plus 2 is true, and then P of A plus 3 is true, and then P of A plus 4 is true. It's this domino effect. Everything after that falls into place. So everything I'm talking about here is weak mathematical induction. Why is it called weak? Well, because people like to make fun of it. But the reason is because of in weak mathematical induction, we use only P of n to prove P of n plus 1. So notice, like, I'm going to make A just equal to 1, so we're talking about something in particular here. But you can start at anywhere to the point. Like we started at 13 for that one proof the other day. So you have 1. So like assuming the base case was 1, we can have something like this. So notice that like to prove P of 3, all we need to know is P of 2. To prove P of 4, all we need to know is P of 3. To prove P of 5, all we need to know is P of 4, right? The way that weak induction works is we use just P of n to prove P of n plus 1. But here's the really weird thing about this. Like, if we're here in this step, like if we're imagine the dominoes falling down and we got to P of 4, and we're trying to prove P of 5, well, we don't only know P of 4 is true, we also know P of 3 is true, we also know P of 2 is true, we also know P of 1 is true. So there's no reason not to necessarily use these to help us prove P of 5. For dominoes, it doesn't really matter, right? Because for dominoes, like if this is the first, second, third, fourth, fifth, sixth, it doesn't really matter what happens to the first 3 dominoes. If the fourth one falls, the fifth will fall. But we could think of some more convoluted examples maybe, where in order for the fifth to fall, maybe the third also has to fall. Like, like the examples I was trying to think of, I was trying to draw these weird things where it was like, imagine like the first domino has to fall to hit the second domino. But then like maybe the first domino is really tall, and then like in order for the third domino to fall, like it has to get hit by the first and the second, something like that. Or maybe like, I don't know, like I was trying to think of wires, like maybe like one goes and does two, but then like to prove two, like three, you need both of them. I don't know. The point is, I hope you could kind of imagine an idea that maybe to show that like the fifth case happens, it would be useful to know that not only the fourth, it might be useful to know that also the third happens, or maybe the second happens, maybe the first happens. So the idea is, in strong induction, we use P of 1 and P of 2 and P of 3 all the way out to P of n to prove P of n plus 1. And it's called strong induction because this is much more information, right? We're using P1, P2, P3 all the way out to Pn. We're using n things to just prove one thing. Whereas in the dominoes and weak induction, we just use one to show the next. Whereas in strong induction, we use everything before it to show the next. Which, why not, right? Because, you know, the way strong induction would work is you have P of 1, and as a base case, you know that's true. And then you use that to prove P of 2. But then the way strong induction works is instead of using P of 2 to prove P of 3, why just use P of 2? You can also use P of 1 in that. So you use P of 1 and P of 2 to prove P of 3. And then to prove P of 4, you get to use P of 3 like usual, but you can also use P of 2, and you can also use P of 1. And to prove P of 5, you can use P of 4, you can use P of 3, you can use P of 2, and you can use P of 1. Does the idea make some sense? Yes? No? How about this? We'll do an example. We'll do a beautiful, nice example, and then maybe you'll see what I'm getting at more here. All right. So let's say we're trying to prove the claim that the claim is the big claim. It's the fundamental theorem of arithmetic. And here's where the fundamental theorem of arithmetic goes. This says that every natural number greater than or equal to 2 can be written as a product of primes. That's the whole fundamental. Actually, the actual fundamental theorem of arithmetic says it can be written uniquely as a product of primes. We're not going to tackle uniquely today. We're just going to prove that it can't be written as primes at all. And we kind of talked about why this should be true before. We talked about like, hey, I mean, you know, if you have 3, or like, yeah, if you have 3 can obviously be written just as 3, which kind of is a product of primes on its own. It's just, I think it's 3 is prime, and just we're kind of multiplying it by nothing, but just on its own, it kind of works. But then if you have like 30, it's not prime. Why is it not prime? By definition, if you're not prime, what's it mean to not be prime?
So to not be prime, it has to be like divisible by something not of itself and one.
Exactly, right? So why is 30 not prime?
It can be divided by 10.
Yeah, 30 can be divided by 10, right? 30 equals 3 times 10. Okay, nice. We said that 3 is a prime. Is 10 prime?
No,
Why is that, Sava?
it's because it can 2 and 5 multiply to 10.
Yeah. Because 10 equals just 2 times 5. So here's the idea kind of outlined before. The idea was just, if something's prime, well, then it's prime. So it can be written as itself, which is a product of primes kind of on its own. If it's not prime, well, then clearly, by definition, it can be broken into two smaller numbers. And this smaller number here, right, 10, either those are both prime. If they're both prime, well, heck, you just have multiple primes. But if one of them's not prime, we'll keep breaking it down. And you should be able to keep breaking it down until you get to a prime. Because if you weren't a prime, you could keep breaking it down further. So that's the idea. And now let's talk about loosely how we might prove this. And notice this feels very induction-like, right? It's kind of like we're saying we can prove 30 is prime. Or sorry, we can prove 30 can be written as a product of primes because we know 3 and 10 can be written as a product of primes. There feels like, yeah. So stick with me for a second. I'm not going to write the formal claim. I hope we understand what I'm talking about. Actually, I'll write it. Formal. This is just saying that for all n and n, there exists a P1 through Pk in primes such that n equals P1 times P2 times P3 all the way up to Pk. And by the way, this right here, I should introduce each of these variables separately, but actually writing this down totally formally is a bit of a pain because what's kind of like we don't know what k is, like how many there exist sign there are. So that first you have to introduce k, and then you have to introduce a whole bunch of things. So I'm just gonna, to avoid confusion, I'm just gonna do this. I think we all know what it means, but it's not technically formal. Anyway, let's go ahead and try to prove this. Oh, actually, I want to say for all n, because it's not for all n, right? Because 1 can't be written as a product of primes. We said for all numbers greater than or equal to 2. So for all n, I'll say in the set x and n such that x is bigger than or equal to 2. There we go. So proof. I'm going to say proof by induction. Not going to put weak or strong yet because let's talk about what we need here. Proof by some kind of induction. Base case. So the idea that I want to explore to prove this is that, hey, like if we can show that 2 itself is a product of primes, right? 2 itself just equals 2. And 3 is a product of primes, it equals 3. But then 4, right? 4 all of a sudden is 2 times 2, right? 5 equals 5. 6 is 2 times 3. 7 is 7. 8 is 2 times 2 times 2. 9 equals 3 times 3. 10 equals 2 times 5. These are all the prime decompositions for each of these numbers going through. And here's the thing to notice, right? At each step, either you're prime, or if you're not prime, like if you're 4, you're 6, you're 8, you're 9, you can be broken down into smaller numbers. So maybe 8 I should have written instead as 2 times 4, right? Which equals 2 times 2 times 2. The point being that if you're not a prime number, you're guaranteed, yeah, I'll do 12 too. 11 is just 11, and then 12 is 2 times 6, which is 2 times 2 times 3. The point being, if you're not prime, you're guaranteed to be able to be written as 2 things multiplied by each other, right? 4 is 2 times 2. 6 is 2 times 3. 8 is 2 times 4. 10 is 2 times 5. 12 is 2 times 6. But because we have 2 things multiplied by each other, right? 2 and 6, 2 and 4, 2 and 3. Notice these 2 things are smaller than the number you started with. So, for example, once you get to 12, if you know that everything less than 12 can be written as a product of primes, well, that means 2 times 6, since 2 and 6 are less than 12, must be able to be written as a product of primes. 2 is just going to be 2, 6 is 2 times 3. So once you get to any number, if you know all the numbers before that can be written as a product of primes, then it's guaranteed that that number can be written as a product of primes. Does that make sense? Again, crickets. I can't tell. Does it not make sense, or do you guys just, is it tenuous? Where Tor was that thumbs up to a make sense or thumbs up to a not make sense?
Makes sense.
Yeah, I hope this makes sense. And so here's the idea. We're gonna start with the base case. We're gonna say base case, notice that n equals 2, because we start at 2, right? N equals 2. 2 is prime. So 2 equals 2 is a way to write 2 as a product of primes. Real simple. 2 just starts off fine. Inductive step. Here's the idea. I'm going to erase this to give some more room. Let's say we try to prove this with weak induction. We try to prove this with weak induction. If we used weak here, then we'd want to show that for all n greater than or equal to, P of n implies P of n plus 1, where P in this case is, you can write it as a product of primes. So, i.e., we want to show that for all n greater than or equal to 2, if n can be written as a product of primes, then n plus 1 can be written as product of primes. All right, so we're trying to prove that, right? Let's just go ahead. It's an if-then statement, right? You assume P of n, you try to show P of n plus 1. So let's let n be greater than or equal to 2 and assume n can be written as product of primes. Thus, there exists a P1 out to PK in the set of primes such that n equals p1 times p2 times pk. Now remember, from this hypothesis of p of n, we want to show that if n can be written as a product of primes, we want to show n plus 1 can be written as product of primes. How can we do that? I mean, let's maybe consider n plus 1. Here's the thing. If we know that n equals p1 times p2 all the way out to pk for some primes p1 through pk, can we say anything about n plus 1? I hope no response vacuously kind of means no, question mark? Because we can't, I mean, we do have a proof in class actually saying that since we know P1 divides n, it won't divide n plus 1. Because P2 divides n, it won't divide n plus 1. So none of these primes will divide n plus 1. But we can't say anything about primes specifically dividing n plus 1. Because the whole idea of this proof that we want to capture is that we know n plus 1 is either prime or composite. If it's composite, it could be written as some like a times b, where a and b are less than n plus 1. But we don't know that a and b are going to be n. A and b are going to be some number less than n plus 1, but it might not be n. It won't be n, in fact. And so knowing that n can be a product of primes, it can be written as a product of primes, is not enough to show that n plus 1 can be written as a product of primes. We need to know that every number less than n plus 1 can be written as a product of primes. Because once we know that, then we know a and b must be able to be written as a product of primes. Therefore, a times b, just put those products together and you have it. So we don't want to use weak induction. Because just knowing it works for n is not enough to know it works for n plus 1. We want to use nice strong induction. By strong induction. And for strong induction, we get to assume more. For strong induction, we want to show that for all n greater than or equal to 2, you still want to connect it to 2. P of 2 and all about the P of n imply P of n plus 1. So I want to show that everything being true from 2 to n implies it's true for n plus 1. So i.e. we want to show for all n greater than or equal to 2, if every integer from 2 to n can be written as a product of primes, then every integer, or then n plus 1 can be written as a product of primes. That's what we're trying to show. Because if we can show this, and we know it's true for 2, well, then it's got to be true for 3. And then if we know it works for 2 and 3, then we can show it works for 4. Then we know if it works for 2, 3, 4, we can show it works for 5. If it works for 2, 3, 4, 5, it works for 6. If it works for 2, 3, 4, 5, 6, it works for 7. I feel really bad for people watching this on double time right now because it's really, really fast. But the point is that this is induction, the exact same idea, except instead of having one domino hit another domino, you have like in dominoes hitting the n+1 domino all together somehow. I don't know how to draw that. I'm sorry. But the point is, yes, this is the idea. So let's just prove it. And the proof we already went over. So now, we have an if-then statement, right? Where the domain's all in greater than or equal to 2. And it's just the hypothesis here isn't P of n, but it's P of 2 all the way out to P of n. Let's go ahead and let n greater than or equal to 2. And assume that for all k and z, such that 2 is less than or equal to k, less than or equal to n, k can be written as a product of primes. And actually, I don't want to use, I'm going to use m here. You can use k. You can use k. I'm going to use m, so I want to use k for something else. The point is, this is just saying exactly what we said before. Just for any number between 2 and n, we can write as a product of primes. Now consider n+1. Here we go. What are the options for n+1? Like, for example, if we just, like we said, 3 was an easy case, right? If we're trying to write 3 as a product of primes, what do?
You write 3.
Just write 3, right? If you're trying to write 5, just write 5. So what's the easy case?
That n is prime.
Yeah, if n+1 is prime. If we're talking about n+1 now, right? Yeah, so n+1 is prime, it's easy. So let's say, note. Actually, let's divide into cases. Either n+1 is prime or composite. So we'll divide into cases. And case 1 says, we're going to assume n+1 is prime. Is prime. Then n+1, which equals n+1, it is already a product of primes. A product of primes. That's the easy case. The harder case is if we assume n+1 is composite. So if n+1 is composite, what we say happens, Safa, or anybody, but Safa was already, Safa kind of owns this from before.
If it's composite, it can be divided by like multiple things other than itself and 1.
Yeah. Assume n+1 is composite. And by definition of composite, there exists some A in N such that, look at that, the table's already working, such that A is, such that 1 is less than A, which is less than n+1, and A divides N. Right? It just means a non-trivial divisor. Something divides that's not one in itself. Thus, N equals AB for some B and N by definition of divides. Right? If A divides N, well then, you know, there's some integer A times B that equals N. Now here's the key. I guess further, I'm just gonna say technicality missing. We need to show that 1 is less than B, less than N. And we can show that kind of easily. It's just kind of because, well, since N equals A times B, then N over A equals B. And because we know 1 is less than A or less than N plus, or N plus, sorry. I'm sorry. It's all N plus 1. What am I doing? We're trying to prove N plus 1 is, we know N plus 1 is composite, not N. So A divides N plus 1. Thus, N plus 1 equals AB for some B and N. Yeah. So we want this to be less than N plus 1. The point is we can kind of show it easily based on this thing right here. I don't want to waste our time doing that. Let me know if you want to see that later. So here's the key though. So now we need to show, yeah. So we're just gonna assume that 1's less than B, less than A plus 1 like we want. Or maybe I should say 2 is less than equal to B. Yeah. The point is, N plus 1 equals, where did I write it? N plus 1 equals A times B, where both A and B are between 2 and N. And we're assuming that we know that everything less than N can be written as a product of primes, right? Everything between 2 and N can be written as a product of primes, right? That's the whole assumption. That's all the dominoes leading up to N plus 1. So thus, or I'll say therefore, because I already said thus, by induction, or by our assumption, since 2 is less than or equal to A, less than or equal to N, and 2 is less than or equal to B, less than or equal to N. And by the way, here I wrote 1 is less than A, less than N plus 1. But since A is an integer, if you're bigger than 1, well, that means that you're at least 2. And if you're less than N plus 1, that means you're at most N. Oh, that makes sense, right? Like the biggest number less than 5 is 4. And the smallest number greater than 1 is 2. Anyway, yeah, so we have this right here. Yeah, so by assumption, since 2 is less than A, less than equal to N, and 2 is less than B, less than equal to N, we know that B can be written as product of primes, and A can be written as product of primes. Hence, if we actually write them out, A equals P1 all the way out to PK for some primes P1 through PK, And B is Q1 times Q2 all the way out to QT for some, I'm going to write QT in orange. If anyone gets that joke. And then for some, for children. And then for some Q1 all the way up to QT primes. So we know that A can be written as this project primes, P1 times P2 all the way to PK. And we know that B is this project primes, Q1 times 2Q all the way up to QT. So how do we know that M? So how can we use it to show that M plus 1 is the product of primes?
Is this just the product of A and B is also a product of primes, or?
Yeah, I mean, we know M plus 1 equals A times B. And so then just note A times B equals P1 times PK for A times Q1 times QT by substitution. Thus, M plus 1 equals AB is a product of primes. Done. Done. This is so beautifully recursive. I love it. It's the idea that all we really did to connect this to the truth is show that 2 was prime. And then after that, all we had to do was show that for any number, if everything before it is a product of primes, then it itself will be a product of primes. And we did that beautifully because either it's prime, in which case it's easy, or it's composite, in which case it can be multiplied by 2 things that are less than it. Those 2 things have to be product of primes because of our assumption. Therefore, it has to be a product of primes. And then that means just it's got to keep going. That means 3 is guaranteed to be prime. 4 is guaranteed to be prime. 5 is guaranteed to be prime. 6 is because everything before it is. 7 is because everything before it is. 8 is because everything before it is. On and on and on and on and on. So you prove for all integers. So I guess there's one last line here that just says, and I'll say last line. And it would say, therefore, by strong induction, every natural number in greater than 2 can be written as a product of primes. So really a square belongs here. Any questions? Okay. So let's do another one of these strong mathematical induction proofs before we leave. And the proof goes like this. Here's the claim. So the claim is, what's a good claim color? The claim is, just want to get this right. Where did I write it down? There we go. Actually, the claim's about this recurrence. So I'm going to define a sequence. So the sequence is going to go like this. We're going to have A0 equals 1 and A1 equals 0. So we have 2 base cases for our recursive case. And then we're going to have AI is going to equal AI minus 1 plus AI minus 2. Actually, I'm sorry. I wanted to have 1 and 2 here. There we go. AI minus 1 plus AI minus 2 plus I for all I greater than or equal to 2. So here is the sequence. And then my claim about this sequence is that for all I greater than or equal to, for all I in the set of integers such that x is greater than or equal to 0. So for all integers greater than or equal to 0, AI is even, I is even, and AI is odd, or I is odd and AI is even. So just saying that I will be the opposite of AI. The index will be the opposite of whatever the actual thing is. That's the weird claim about this weird set of things. And let's just look at a couple, right? I mean, A0 equals 1. 0 is even, 1's odd. That checks out. A1 equals 1. Or sorry, A1 equals 2. 1 is odd, 2 is even. That checks out. A3 is the first interesting one. This is going to be, so the way you make the next terms in the sequence is you add the two previous terms and you add the index. So here the two previous terms are going to be 1 plus 2 plus the index is 3. So 1 plus 2 is 3, 3 plus 3 is 6. 3 is odd, 6 is even. A4, we're going to add the two, oh, I'm sorry, wait a minute. Sorry, man. We add the two previous terms and we add the index of 2. So we get 2 plus 2 is 1, we get 5. So 2 is even, 5 is odd. A3, we add the two previous two, we get A1 plus A2 plus 3, which is A1 is 2, plus A2 is 5, plus 3. That's 7 plus 3, which equals 10. So again, odd, even. So it looks like this always works. And why would this always work? Well, this seems to always work because notice that every two consecutive numbers, like these two, these two, these two, are going to have opposite parity. So 1 and 2, 1's even, 1's odd. 2 and 5, 1's even, 1 odd. 5 and 10, 1's even, 1's odd. So when we go to calculate an plus 1, which equals an plus an minus 1 plus n plus 1, an plus an minus 1 is going to be odd. There's going to be an odd plus an even or an even plus an odd. They're going to be opposites is the point. It's going to be odd. And then an odd plus an even is an odd, and an odd plus an odd is an even. So an is going to be the opposite of whatever n plus 1 is, which is exactly what we wanted to show. We wanted to show they'd be opposites. So if n plus 1 is even, the whole thing's even. If n plus 1 is odd, the whole thing is odd. So assuming that an and an minus 1 work in the sense that they'll have opposite parities of their indexes in n minus 1, well, then we know it's going to work for n plus 1. And that's the chain reaction. That's the induction. So I'm going to prove it real quick. Proof by strong mathematical induction. We're actually going to skip the base case and come back to it because it's a little interesting. Let's do the inductive step. So here the inductive step. We want to show that for all n greater than or equal to, I'm going to say 2. P of 0 all the way out to P of n implies P of n plus 1. Why do I start at P of 0? Well, because remember, we want to show this for all integers greater than or equal to 0. So we want this to be true for all integers greater than or equal to 0. So in the base case, we're going to want to show P of 0 is true. Here's the thing. We're also going to want to show P of 1 is true. And you'll see that in a second once we do this argument. So let's do this argument first. So I want to show for all n greater than or equal to 2, P of 0, P of n implies P of n plus 1. i.e., we want to show that for all n greater than or equal to 2, for all n greater than or equal to 2, actually, we're using I here, so I use I. So I want to show for all I greater than or equal to 2, if k is even and ak is odd, or k is odd and ak even for all 0 less than or equal to I, k less than or equal to I, then n plus 1 is even, or then I plus 1 is even and a of I plus 1 is odd, or I plus 1 is odd and a of I plus 1 is even. This sounds really complicated. Let's just write down the claim. All we're trying to say here is that for every integer, we want to show that for any I greater than or equal to 2, if we can show that the claim is true for everything between 0 and I, then it'll be true for I plus 1. That's the induction, because then once you have that, you can prove the next one, the next one, the next one. So here's how we're going to do that. Let I be greater than or equal to 2. Let I be an integer such that I is greater than or equal to 2. Then I'll say consider a of I plus 1. A of I plus 1. So notice that since I is greater than or equal to 2, actually, I'm going to use 1 here. Let's see why in a second. I could use 2, I'm going to use 1. Since I is greater than or equal to 1, I plus 1 is greater than or equal to 2. Why is that important? That's important because by our definition here, since I plus 1 is greater than or equal to 2, we can use this formula to compute AI plus 1. So, thus AI plus 1, because I plus 1 is greater than or equal to 2, we can use it here to show it's the 2 previous. There's going to be AI plus 1 minus 1 plus AI plus 1 minus 2 plus the index, which in this case, AI plus 1 minus 1 is just AI. AI plus 1 minus 2 is AI minus 1 plus I plus 1. So here's the key. The key is because I is bigger than or equal to 1, I plus 1 is bigger than or equal to 2, so we can calculate it using our recursive formula right here. And by our assumption, AI and AI minus 1 kind of follow our claim, meaning if AI is even, AI or I will be odd. Oh, sorry. If I is even, AI will be odd. If I is odd, AI will be even. And same thing with AI minus 1. Note by previous result, I is even or odd. So now I have two cases. Case 1, assume I is even. Then, since zero is less equal to I less equal to I, by our assumption here, where we want to assume that P of 0 all the way up to P of I is true, by this assumption, AI is the opposite parity of I, thus AI is I. So since I is even, and we're assuming this claim holds, or assuming this claim right here holds for all I, for everything between 0 and I, that means that AI must be odd. Further, since I is even, I minus 1 is I. You've shown things like that before. Then, because 0, because I is greater than or equal to 1, I minus 1 is equal to 0. Hence, 0 is less than or equal to I minus 1, which is less than or equal to I. Why is that important? Because again, we see that for everything between 0 and I, our claim up here is true, that the parity of AI would be the opposite of A, or opposite of the index. Thus, by our assumption, AI minus 1 has the opposite parity to I minus 1. Hence, AI minus 1 is I minus 1 was odd. Hence a minus 1 is even. Hence I minus 1 is odd. So all we've shown is in the case where I'm way over. Sorry, people. Anyone can leave whenever they want. I'm going to trim this video down and put it online. It's going to be about an hour. And yeah, but anyway, so the point is, so a minus 1 is the opposite parity to I minus 1. Hence a minus 1 is even, since I minus 1 is odd. Thus, AI plus AI minus 1 is odd because an even plus an odd is odd. So we've shown that if I is even, AI will be odd, and AI minus 1 will be even. So AI plus AI minus 1 is odd. Finally, since I is even, I plus 1 is odd. Thus, AI plus 1, which equals AI, is AI is I minus 1 plus AI, will be an odd plus an odd will be even. It is an odd AI plus AI minus 1 plus an odd I plus 1. So, this might have seemed kind of complicated, but here is the point. The point is, assuming I is even, and knowing that I is greater than or equal to 1, knowing those two things is enough to know that I plus 1 will be odd, and AI plus 1 will be even. So they have their opposites like we wanted. And if we assume AI is odd, we can use basically the exact same proof to show that the exact opposite happens. If AI is odd, then I plus 1 will be even, and AI plus 1 will turn out to be odd. The point being, that assuming that I is greater than or equal to 1, we can assume that I is greater than or equal to 1, and assuming that the claim is true for 0 all the way out to I, we can show P of I plus 1 is true. We can show that the index and the term have to be opposite for I plus 1. AI plus 1 and I plus 1 have opposite parities. And so what I'm going to do is I'm going to just erase this. That's okay. And I'm going to say we're going to have a case 2. I is odd. And by same logic, we can show up right time. By same logic, I plus 1 will be even, and AI plus 1 odd. Thus, in either case, I plus 1 is even, AI plus 1 is odd. Thus, in either case, AI is even, AI plus 1 is even, and I plus 1 odd, or AI plus 1 is odd, and I plus 1 even. Conclusion. Therefore, for all n greater than or equal to 0, or for all I greater than or equal to 0, I and AI have opposite parity. Meaning one's even and one's odd, or the other, or the first one's even, the next one's odd, or the first one's odd, the next one's even. So that was a very long and very convoluted kind of proof of even and odds, but here was the big point. The point is that once I is bigger than or equal to 1, once we know this, we know I plus 1 is bigger than or equal to 2. And if I plus 1 is bigger than or equal to 2, all of a sudden we can use this recursive definition to talk about AI plus 1. That's the key. I plus 1 greater than or equal to 2 means we can use this formula to calculate AI plus 1. And then using this formula was the key, because we had this, and using this formula was the key to show that, oh, okay, it holding for the previous ones will prove it holds for AI plus 1. But we had to start at 1 because we needed to use this formula to do it. And so since we needed to use this formula to do it, we actually just need to show that it works for 0 and it works for 1 just by brute force, because we don't have a clever way to do it because they're just kind of like defined. So that's why we need to show the base case for 0 and 1, and then we start at 1. So we want to show P of 0, and P of 0, we can do that just by saying note 1 is, or 0 is even, and A0 equals 1 is odd. And here we can note 1 is odd. And A1 equals 2 is even. So sometimes in strong induction, you're going to have more than one base case. It just depends on when this chain reaction takes over. This chain reaction takes over once I is bigger than or equal to 1. So that means that to prove 2 is the first one we can prove using the chain reaction. So that means we have to show 0 and 1 by brute force. But I am way over. I'm going to write up this proof all nice and put it online. And I'm going to put out some extra examples if you guys want them to. So does anyone have any questions?
You wanted me to talk to me about stuff, or the...
Yeah, we'll do that. We'll do that in a second, Alex.
Yeah.
All right, no any questions. Sorry for going over. But this has been a great class. I wanted to get this down because I wanted you guys to be able to do your homework. So sorry about that. But like my announcement says, we will have class Monday. We'll be going over a bunch of reviews on this stuff. And then Tuesday, no class. Good luck on the test. No homework next week. So we're going to chill. So sorry for going over, but enjoy your no class day while you're taking the test.
Thank you.